Hello, welcome back to the channel. In this video we are introducing functions. Just so that we are clear going forward, I'm just going to take you through the basic definitions that you need to know about as far as functions are concerned. The first definition that you need to know is what an asymptote or asymptotes are. Asymptotes are basically straight lines that graphs continuously approach but they never touch. We have asymptotes in the case of hyperbolic functions. If we can just look at that to demonstrate how asymptotes look, usually we use dashed lines or broken lines, if I can just put it like that, to demonstrate asymptotes. So suppose these are your two asymptotes. It's either a horizontal one or a vertical one, and then you have a graph like this. As you can see, it keeps approaching the asymptotes at either end, but it will never really touch the asymptote. So that's basically what asymptotes are for hyperbolas. And then we have a situation with exponential graphs. They only have what you call a horizontal asymptote. Exponential graphs only have a horizontal asymptote. Okay, so as you can see, it also continuously approach the asymptote at this end, but it will never really touch the asymptote. Okay, that's basically what an asymptote is, or asymptotes are. The equation of asymptotes, it's either y equals to a certain number or x equals to a certain number. As you can see, for the vertical asymptote, this being the vertical asymptote, and then that being the horizontal asymptote. You can just see which one is a horizontal one, which one is a vertical line. And then exponentials, they only have a horizontal asymptote. The equation is going to be y equals to a certain number. That's the y-intercept. If that is 2, that means y is going to be 2. If that was 3 for the hyperbola, I mean this y-intercept, that means the equation of the horizontal asymptote is going to be y equals to 3. If the what you call the x-intercept was like 2, that means the equation of the vertical asymptote is going to be x equals to 2. That's basically how you determine the equations of the asymptotes. Okay, and then we also have what they call an axis of symmetry. An axis of symmetry is nothing other than just a line that divides the graph into two equal halves. In the case of hyperbolas, it's easier to spot what an axis of symmetry is. For instance, when you have a graph like that, you just have a line which is also a dashed line that divides the graph into two equal halves. That is what they call an axis of symmetry. The equation of the axis of symmetry is given by x equals to minus b over 2a. Just how you determine the equation of the axis of symmetry for a hyperbola. And then, not for hyperbola, I mean for parabola. And then for hyperbolas, we also have the axis of symmetry. It could be, let me use a black line, could be this one. As you see, it divides the graph into two equal halves, and the equation of that is y equals to x plus k. And it could also be this line. That could also be the axis of symmetry, and the equation is given by y equals to minus x plus k. As you can see, the two axes of symmetry, they pass through the intersection of the two asymptotes. So that's always the case when it comes to what you call hyperbolas. Okay, let's move on, because I think those are basically the only two functions that have axis of symmetry, and those are the ways of getting the equations of each axis of symmetry. Okay, we can speak about a decreasing or an increasing function. When they say a function is decreasing, they're basically saying that or maybe a portion of a function decreases. Basically, that portion is where the y values are decreasing when the x values increase. So if we can look at a straight line like this, okay, if I can just put a straight line like this, you can see that as you move from left to right, the y values are increasing on the straight line, as well as the x values are increasing. So that is a decrease, I mean, it's an increasing function. However, if we draw another function like this, and we show the line looking like that. You can see as you move from left to right, the x values are increasing. However, the y values are decreasing as you move in this direction from left to right. So that is a decreasing function. Decreasing, increasing. That's basically how you identify whether or not a function is decreasing or increasing. So you can also maybe tell with a hyperbola if it's a decreasing or an increasing function. Let's look at this parabola rather. This portion, as you can see, the y values are decreasing as you move from left to right, and this portion, the right hand side portion, as you move from left to right, the y values are increasing. So this is a decreasing side, this is an increasing side of the function. So I think now it makes sense what increasing and decreasing is. Gradient basically just refers to the slope or steepness. We are moving on in case you haven't realized. So gradient just the slope or the steepness of a graph, as well as it also indicates the direction as well. So if it's positive, it will show you that this is going in this, but if it's negative, the direction is going to be something of this nature, slanted to the left or slanted to the right, depending on whether or not it's positive. If it's positive, it's slanted to the right. This is for a positive gradient, and then this for negative gradient. And then now we have intercepts. Intercepts, basically these are just points where graphs they meet the x or the y axis. So we have an x-intercept, we have a y-intercept, depending on which axis the graph meets. If it meets the x-axis, we have an x-intercept. If it meets the y-axis, we have a y-intercept. And then we have what they call intersection points. Intersection points, these are just points where two graphs meet. So we can have a parabola, and then we can also have a straight line. These are the points of intersection. Okay, we have an inverse of a function. Inverse of a function basically refers to what? The reflection, or is it the reflection? It is actually the reflection of a graph across the line y equals to x. So if we can just maybe demonstrate that with the drawing, we have a situation like this. This is a hyperbola. This is a parabola, not hyperbola. I keep mixing hyperbola and parabola. I don't know for what reason. But yeah. So suppose you have a line y equals to x here. And then when you reflect this graph across, about that line, what you will have is this. Let me use a different color. You will have this. So that is basically the reflection of the green graph about the, and we use the notation f exponent -1 like that to show that this is the inverse of f. And then for this one, this is f, or they use f at x, and then here we can still use f at x, but with that -1 as the exponent there, to show that the one is the inverse of the other. Basically what happens if you are drawing this thing on a paper, you can try to use your ruler to fold the paper along the line y equals to x, and you will see that when you fold that paper along that line, this inverse falls exactly on top of the original graph. That's basically how you tell that one is an inverse of the other, by making sure that when you fold the line, or when you fold the paper along the line y equals to x, the inverse of the function falls on top of the function itself. Okay, and we have what they call range and domain. Okay, before that, these are just the notations which have been used. I've already explained this: the inverse notation, the original notation. F at x just means y, basically. The y values, they are referred to as f at x values. And the inverse, you know it, the gradient, we just use prime. That's it. There's nothing special about it to show that it's a gradient, the very same gradient that I was just explaining in the past few minutes. We have transformation and turning point. Turning point is only applicable to parabolas or quadratic functions. So it's basically just the point where this graph turns. That's it. and the coordinates, you can get the x coordinate using that, or maybe we'll look at it at a later stage, how to get the coordinates of the turning point when you do some examples. But basically, turning point is just that point where the graph turns. It was going down, now it's going up. It was going up, now it's going down. So that's the turning point. There's nothing special about it. Transformation refers to whether you are shifting the whole graph horizontally or vertically. So it's just about moving the graph upwards or left or down or right or east, west or south, north, whichever direction you're required to move it. So that's just transformation. I think these are the basic definitions that you need to know about, and we see each other in the next video. I hope I've kind of made some sense with regards to some definitions that you need to know. Let's see each other in the next video. Thank you.